Hello everyone, welcome to the Mercury Virtual. Hope you are doing good. Today I am going to continue with chapter number 2, that is floating point, and name of the chapter is representing and manipulating information. Only one topic is left, that is floating point. So I am going to continue with only one topic, that is floating point. But before this, let's take a quick review or quick recap of the previous class, that is yesterday's class. In the yesterday class, we talked about topic number 3, that is your integer arithmetic. Integer arithmetic. So we have started with integer arithmetic, that is arithmetic without any fractions is known as integer arithmetic. Means whenever we take the discrete values, that is known as the integer arithmetic. We say a computer performing integer arithmetic ignores any fractions. Today the topic is floating point. In that we will discuss what is a floating point, but in yesterday's class we talked about what is integer arithmetic. Then we also talked about how we can add unsigned numbers with other unsigned numbers. There are two types of numbers in computer languages. One is unsigned number and another one is signed number. So we have talked about how we can add two unsigned numbers. We also talked about an example how we can add. Simply, if I want to add these two bits, means 4 bits are available, 4 bits are available. If I want to add, then 1 plus 1 is 2, that have a binary 0, 1. So put over here 0 and 1 is your carry. Now add these two bits, that is 0 plus 0 is 0, and then add 0 plus 1, that is your 1. This is known as column 0, this is known as column 1, column 2 and column 3. Means there are 4 columns in this example, column 1, column 2, column 3 and column 4. Or in other sense, column 0, column 1, column 2, column 3. This is the next one. This is then add the 2 bits in column 2. First of all, add 2 bits in column 1. This is column 1, and the carry is 0 because there is no 0. Now add the 2 bits in column 2 plus the carry bit. Summing 1 plus 1. This is 1 plus 1. This is 1 plus 1. This is summing 1 plus 1 plus the carry 0 results in 0 with the carry of 1 to column 3. Suppose if I add 1 plus 1, that is 0, 0 plus 0 is 0 and the carry is 1. Now there are three ones. This is 0, 1, 0, 1. There are 3 ones. Finally add the 2 bits in column 3, that is 1 plus 1 plus the carry bit. This is summing 1 plus 1 plus the carry 1 results in 1. As I told you, 1 plus 1 is 0, 0 plus 1 is 1 plus carry 1. And we have to discard the last digit, that is your leftmost digit, because here in this example, there are only 4 bits for addition purpose. So in answer or in solution, there will be only 4 bits, not more than 4 bits. So we have to discard the leftmost bit, that is 1. This is mentioned. Since we add in hardware, the output usually has the same number of bits as the number of bits being added. Since we are adding a 2-bit UB number, the result should be a 2-bit result. So we have to discard the last digit, that is 1. And then we have talked about how we can add the 2's complement number. How we can calculate the 2's complement? First of all, find out the 1's complement by inverting all the digits, inverting all the bits, and then add 1 to the inverting bits. Suppose I have 4 bits, 1 0 1 0. So the first complement is 0 1 0 1, and then add 1 to the inverting bit, that is 0 1 0 1. This says 2's complement is a mathematical operation on binary numbers as well as binary signed integers based on this operation. Its wide use in computing makes it the most important example of a radix complementation. Then how to add in 2's complement? This is the example. This is a simple example. This is the example of 2's complement. 56, first of all convert into bits. Then 19, first of all find out the 2's complement of 19. That is 11011101. Then use the sum of operations. Means 0111000. This is 0111000, and then add 19 to this bits. Means use this one 1101101. This is 1101101. Add these two bits. Means simply add these two bits using the same operation. 1 plus 1 is 0, 1. 1 plus 1 plus 1 is 1 0 or 1 1. So use all this, and that gives the output, that is 0 1 0 0 1 0 1. Because I have to discard last one digit, because the input is 4 plus 3 7 bits and the output is in 8 bits. So we have to discard the last bit, that is leftmost bit. So the output is 0 1 0 0 1 0. So 0 1 0 0 1 0. Next, we have also discussed another example how we can add the numbers. These are both in 2's complement. So first of all find the 2's complement of 35, then find the 2's complement of 58, then add these two numbers. Then we also talked about how to use the 2's complement negation. Negation means how we can convert the bits of one form to the another form. This says negation of a 2 bits complement number is accomplished by inverting the bits and then adding 1. Inverting the bits means changing the bits from 0 to 1 and 1 to 0 and then adding the number 1. This is the example. This is 310. The output is 0 1 1, but we have to add the leading zeros, and minus 310 is 1 1 1 1 0 1. First of all find inverting the bits. All zeros are converted into ones and ones are converted into 0, and then add 1 to the bits. This gives the output this one. So this is minus 310. Because the input is 310, its negation is minus 310. Now here the input is minus 310, so the output is 310. Means inverting the bits, that is known as the 2's complement negation. Then we talked about how to multiply the unsigned numbers. This is a simple procedure. First of all, use 1 and multiply by all the digits, all the bits, 1000, then 0, this one, this one. Now, sum of these bits step by step. Means first of all, add these two bits, then the output must be added to another bits, then the output is added to another bit. So this is done by step. This is the example how we can multiply the 2's complement. This is the example, minus 1111. Then add the unsigned addition and use the step-by-step procedure for adding the values. So in simple terms, when we multiply the bits, first of all multiply and then add the values step by step. So this is what we have covered in yesterday's class. In today's class, I am going to continue with floating point. System is so much. Today I am going to continue with next topic, that is fourth topic, your floating point. In the last class we discussed how we can calculate in integer, means there is no fraction. Now the same reverse of the yesterday's topic, that is your floating point number. So this is nothing but a reverse of the previous class, that is in last class we discussed integer, in today's class we discussed floating point. So first of all, meaning of floating point. Floating point is nothing but when we use decimal point, that is we use 2.34, that is after 2 there is a decimal point, so that is known as the floating point. So whenever we take discrete values that are known as integer, and whenever we take decimal values that are known as floating points. This is a floating point representation encodes rational number of the form v equals to x into y. It is useful for performing calculations involving very large numbers. Means whenever we have to calculate or whenever we have to do the calculations that involves very large number, that can be done by the floating point representation. Now let's see in with the help of PPT what is floating point. This is floating point. In computing, floating point describes a method of representing an approximation of real numbers. Real number means 1, 2, 3, 4, all the positive numbers, in a way means we can represent it as an approximation. Suppose if I want to use the approximate of 4.5, so that is your 5. So we can use the approximation of the real numbers in a way that it can support a wide range of values. The numbers are in general represented approximately to a fixed number of significant digits. Significant digits mean signed numbers as well as unsigned numbers, and scaled using a exponent. There are two terms, one is exponent, one is your mantissa. So whenever we take decimal numbers that are known as exponent. Next line says the base for scaling is normally 2, 10 or 16. As I told you in the previous classes, there are different kinds of number system. So 2 is denoted by binary number system, 10 is decimal number system, and 16 is hexadecimal number system. So the base for scaling is normally either 2, 10 or 16. Next say the typical number that can be represented exactly is in the form of, or exactly is the form significant bits or significant digits into base per exponent. So this is the main form of floating point. Means how we can represent the floating point. Simply use significant bit and multiply by base and then par to the exponent. There is no whole par. This is a par only to base, that is exponent. This is how we can represent floating point in MS or in computer system. Next say IEEE 745. There is a organization, there is a standard that is known as IEEE, that is Institute of Electronic and Engineering Applications. I'm repeating again, Institute of Electronic and Electric Engineers. Institute of Electronic and Electric Engineers. So IEEE is a standard or maintains a standard with which we can use the protocols which we can use in computer. So IEEE has standardized the computer representation for binary floating point in IEEE 754. This is a version for floating point. aka IEC 60559. So this is another name for IEEE 754. This standard is followed by almost all modern machines. Notable exceptions includes IBM mainframes. Means this standard. This standard means IEEE 754, that is floating point, that is developed or represented by IEEE, that is Institute of Electric and Electronic Engineers. So this standard is followed by almost every computer except IBM mainframes, which supports IBM own format, in addition to the IEEE 754 binary and decimal format. Means except IBM mainframe computers, all the organizations uses only IEEE 754. But IBM uses on its own formats, and Cray vector machines where T90 series had an IEEE version, but the SP1 still uses Cray pointing floating point format. This is how we can represent the number in floating point. There is a standard known as IEEE that maintains the standard for floating point representation. This standard or the standard provides for many closely related formats differing in only a few details. 5 of them formats are known as basic formats and other are termed as extended formats. And there are multiple types of format that is used in IEEE 754, and 5 of them are known as basic format and other are known as extended format. There are some basic formats and other are extended formats. 3 of these are especially widely used in computer hardware and languages. Computer languages means C, C++, Java. So these formats are generally used in computer hardware and languages. Now, what are these types of formats? Means IEEE developed what type of formats? First one is single precision. That is single precision. Usually used to represent the float type. As I told you, whenever we have to represent the decimal point in basics of programming, so we use the float data type. So that is known as single precision. In the C language family, though this is not guaranteed. This is a binary format that occupies, so float point is a binary format, single precision is a binary format that occupies 32 bits. 32 bits means 4 bytes and it's significant as a precision of 24 bits, that is 7 decimal digits. Next standard format is double precision, that is usually used to represent the double type in the C language family. Double type means this is a data type that is used to represent the double data type in C language family. This is a binary format that occupies 64 bits, that is 8 bytes, and its significant has a precision of 53 bytes, that is about 16 decimal digits. Next one is your double extended. So first one is your basic format is your single precision, then double precision, and then next one is your double extended precision, also known as extended precision format. This is a binary format. This is a binary format that occupies at least 79 bits. 79 bits means 80 of which the intact implicit bit rule is not used. And its significance has a precision of at least 64 bits. So these are the multiple bits that is available. You have to see how many bits are used for precision and how many bits are used for binary format. Next is a format satisfying the minimum requirement, that is 64-bit precision, 15-bit exponent, thus fitting on 80 bits. This is how we can represent multiple formats with the standard IEEE 754. This is IEEE 754. So if I calculate the crux, so I am starting with floating point. Floating point is nothing but when we represent the number in decimal form, that is known as floating point. This is the syntax, this is the equation for floating point number. And there is a standard for organization that maintains the standard, that is known as IEEE. IEEE also maintains the standard for floating point, which we are using in modern computers, that uses by all the organization except IBM mainframe computer that uses its own format. And this format also provides basic formats like some basic formats, some extended formats. And some basic formats include single precision, double precision, and double extended precision. This is a floating point. This, as you see, this is IEEE 754, a careful crafted standard for representing floating point numbers and operations performed on them. And the full form is Institute of Electrical and Electronics Engineers. Now, next topic is your fractional binary numbers. How we can calculate the binary numbers with the help of floating point representation. This says in mathematics and digital electronics, a binary number is a number expressed in binary numeral system or base 2 number system, which represents numeric values using two different symbols, either 0, either 1. More specifically, the usual base 2 system is a position national bit with a radix of 2. As I told you, there is a number system that is known as binary that has a base 2 number system. Because of its straightforward implementation in digital electronic circuitry using logic gates, the binary system is used internally by almost all modern computers and computer-based devices such as mobile phones. Means this paragraph says there is a binary number that is known as base 2 number system that is represented by either using zeros and ones. This is used internally by all modern computers and computer-based devices such as mobile phones, and each bit is represented or each digit is represented by either 0 and 1, that is known as bits or bit. Now, how we can calculate, how we can represent the fractional binary number. Next topic is your fractional binary representation. This is your most important topic. This says binary representation of fractional number is very similar to decimal representation. How we can represent decimal? Using either 0 to 9. For example, let's look at the following decimal fraction number. This is a fraction number. This is 0.567 base 10. If I want to represent 5, then using after the door, this is 5 by 10, then goes to the next place, that is 6 by 100, goes to the next place, that is 7 by 1000. If there is another number, then 10,000, and so on. So I can write 5 into 10 power minus 1, because whenever in denominator there is any number and I want to represent in numerator, so that is denoted by minus 1. This is 5 into 10 power minus 1 plus 6 into 10 power minus 2, because 100 is also known as or also used as 10 power 2, and this is in denominator, and whenever we put in numerator, so this is 10 power 2 minus 2 into 6, then 7 into 10 power minus 3, because 1000 is 10 power minus 3. So this is how we can represent the binary numbers with the help of fractions. The same we can see in the binary fractional representation. This is the same example. This is 1 by 2, 1 by 4, 0 by 8, 1 by 60. This is the decimal number and this is the binary representation. Because decimal uses 10, so we can use 10, 100, 1000. Because binary uses 2, so I can use 2, 4, 8, 16, 32, 24, 32, 64 and so on in terms of 2 figures. This is how we can represent the number. This actually means that decimal fraction with one digit after comma can represent 10 power 1 fraction number, with 2 digits after comma 10 power 2, with 3 10 power 3 and so on. So this is what what I said. This is 10 1, 10 2, 10 3, 10 1, 10 2, 10 3. The same is in binary representation with one digit after comma is minus 2 1. This is 2 power minus 1, 2 power minus 2 or 2 power 2 and so on. But it is very difficult to understand that because decimal and fraction are different in size. As I told you, binary number system have a base 2 and the range 0 to 1. In the same way, decimal has a different part. So it's different in their size. They very frequently cannot represent each number with equal amount of digits after comma. For example, 0.5 base 10 equals to 0.1 base 2. But 0.4 is this one. So that is why you should always consider a problem of precision. This paragraph says there is a difficulty whenever we have to calculate the same number into decimal number and into binary number. So it is very difficult to calculate the number with the same number with the help of binary number and with the help of decimal number. Now let's see example how we can calculate the how we can calculate or how we can represent the binary representation. Suppose I have to use this one, same example. Suppose I have to represent 0.123. This is in decimal form. I have to represent this number, right? This is 2. So first of all, uses after door. This is 1 by 10 power 1 plus 2 by 10 power 2 plus 3 by 3 upon 10 by 3. So if I want to represent within numerator, this becomes 1 into 10 power minus 1 plus 2 into 10 power minus 2 plus 3 into 10 power minus 3. So this is how we can represent the fraction number. My question is that I have to represent this number into fraction form. So first of all, starting with the door, that is decimal point, use 1 upon 10 power 1 plus 2 upon 10 power 2 plus 3 upon 10 power 3. And whenever we have to put this into the numerator, that is denominator into numerator, so the power becomes minus 1. This is 10 power minus 1, this is 10 power minus 2, this is 10 power minus 2. This is how we can represent the binary number or decimal number into the fraction number. Fraction number means that is using after decimal point. Now, next topic is binary functions. So first of all, let's see your book. This is a fraction binary number. This is how we can represent. This is 10 power minus 2 into 4, 10 power minus 1 into 3, 10 power 0 into 2, 10 power 1 into 1. So this is how we can represent 12. The example is 12.34. So first of all 1, that is 10 power 1. Now let's see this example. Example is saying 12.34. So this is the same part as we done in the binary addition or binary conversion. The same procedure. Use 10 power 0 into digit plus plus 10 power 1 into 1, the same procedure. But if I am using after door, so this is 3 upon 10 power minus or 10 power minus 1. Then plus 4 upon 10 power minus 2 or 10 power 1. This is not minus 1, this is not minus, this is 2, and whenever it goes to the numerator, this becomes 10 power minus 2 and 10 power minus 1. Means in simple terms, if I have to represent this number, this is only integer number. So the procedure is same. But if I have to represent 0.34, so the procedure is different. Use 3 upon 10 power 1 and 4 upon 10 power 2. This is how we can represent the number. This is the same example, 12.34. This is 10 power 0 into digit, 10 power 1 into digit, plus 3 into 10 power minus 1, plus 4 into 10 power minus 1. This is represented by 12, 34 by 100. This is how we can represent fraction binary numbers. This is another example, 1011.2. This can be represented. This is a fraction binary. This is another example. First of all, let's see the slides. First of all, let's see the slides, then you understand these concepts. Next is your binary fractions. In binary, with the columns heading, that is 2 power minus 1 equal to 1 by 2, 2 power minus 2 equals to 1 by 4, and so on. Means in decimal we represent by 1 by 10, 1 by 100, 1 by 1000. In binary we can represent 1 by 2, 1 by 4, 1 by 8, 1 by 16 and so on. The number 12.75 in an 8-bit binary with 4 bits after the binary point is therefore represented as 8 plus 4, because this is 2 part 0 into 1, this is 2 part 0 into 1 and then 2 part 2 into 1. This is 8 plus 4 and 0.75 is represented by 0.5 plus 0.25. Because after decimal, first one is 1 by 2, that is 0.5, 1 by 4, that is 0.25. And here, this is your numbers, this is 12, this is 1, 2, 3, 4, 2 par 0, 2 par 1, 2 par 2 and 2 par 3. This is how we can represent the number in binary format. Notice that for the same number of bits after the point, the binary fraction provides less accuracy. So this is one of the limitation of binary number, that this provides less accuracy as compared to the decimal point number. It can only take 4 different values, whereas a decimal value can have 100 different values with 2 digits. You will see in a moment how this can cause trouble. Means these values can cause trouble whenever we use in computer organization. This provides less accuracy as compared to the decimal point number. This is the example 12.74. The output is 8 plus 4 plus 0.5 plus 0.25. Now, let's take the example how we can convert decimal into the binary number. So, suppose my example is 6.125. So, this is 4 plus 2 plus 0.125. This is 6, that is known as 4 plus 2 and then 0.125. But what about this more interesting number is 6.4. Now let's see with the help of book how we can represent. This is how we can represent the binary number. This is the example. Suppose I have to represent the binary number, that is 101.112. 10.1112. First of all, use same concept, that is 101, 1 into 2 par 0, 1 into 2 par 1. This is 1 plus 2 par 0 into 1, 2 par 1 into 0, 2 par 2 into 1. This one is, I think, extra. Yeah. Plus, this is the 1 into 2 par minus 1, 1 into 2 par minus 1. And then sum up, this is the output. Now, let's take this example with the help of pen and I will explain you in a better way. Suppose I have to represent the number. This is a number 101.11. Right. This is a dot. I have to convert or I have to represent into decimal form. So first of all, use binary number. This is a binary number and this is a decimal number. So 0.11 is decimal number and 101 is your binary number. So first of all, take binary number. Use same representation. 2 par 0 into 1 plus 2 par 1 into 0 plus 2 par 2 into 2 par 2 into 1. So this is 4 plus 0 plus 1, that is your 5, right? So this value has a 5 output. Now use 1.11. This is I will explain. I have explained you in previous classes, already explained, right? Now this is your new concept, 0.11. First of all, use 2 par minus 1 into 1. Now here we go from right to left, but here we go from left to right. This is from right to left, this is from left to right. Use 2 par minus 1 into 1 plus 2 par minus 2. Means whenever we go from right to left, the power automatically increases. This is 2 power minus 1 into minus 2 into 1. This is 1 by 2 and this is 1 by 4. Now take the LCM. We can take the LCM. This is sorry, the LCM is 4, this is 2, this is 1. So the output is 3 by 4. So I can represent the output 5, 3 by 4. This is how we can represent the output. I'm repeating again. My question is that I have to convert this fractional digit into decimal digit. So first of all, take integer value, that is 101. Uses the same concept, 2 power 0 into 1, 2 power 1 into 0, 2 power 2 into 1. Goes from left to the right and the output is 5. Now use decimal part. Instead of using 2 power 0, I am using 2 power minus 1 and goes from right to the left. So 2 power minus 1 into digit, that is 1, plus 2 power minus 2 into digit, that is 1. So 2 power minus 1 is 1 by 2, 2 power minus 2 is 1 by 4. Now put these 1 by 2 plus 1 by 4, then take LCM. This is 2 plus 1, that is 3 by 4. So the output is 3 by 4. Now represent both values, that is 5, 3 by 4. So this is the output. This is the output, same output, that is 5, 3 by 4. This is how we can represent the fractional binary number. Now let's take another example. Suppose my number is 100.0100, right? Suppose there is another number 0. So first of all, divide into convert into this, which form? Decimal form, right? So first of all, take only the integer value, that is 0, 1, 1. Here this side. Here this side using, here this side I am using sorry for network problem. Now it is audible to you. So this is how we can represent. First of all, divide integer and fraction into different parts. This is the integer and this is the fraction, that is 0, 1, 0, 0. Now calculate in a separate way. First of all, use this one. Hello, are you able to hear me or not? So first of all, divide these separate two numbers, that is your integer number and fraction number. This is your integer number and this is your fraction number. So use first of all this one, that is 2 power 0 into 0 plus 2 power 1 into 0 plus 2 power 2 into 1 plus 2 power 3 into 0. Now calculate these values. First of all 0, then 4, then 0, then 0. So the output is only 4. This is the output, that is 4. Now next part is your, now I am using 0, 1, 0, 0, that is your fractional part. So use it 2 power minus 1 into 0 plus 2 power minus 2 into 1 plus 2 power minus 3 into 0 plus 2 power minus 4 into 0. So this is how we can represent starting from right to left. This is 0 and that is 1 by 4 because 2 by 2 is 4. So this is 4 by 4 and again 0, 0. So the output is 4, 1 by 4. So this is your main output. This is the way how we can represent the decimal form, how we can convert the binary form, binary number into the decimal form. The procedure is that first of all divide or bifurcate into two parts. One is your integer part, one is your decimal part. First of all use or calculate integer part by using the same concept, and then uses fractional part by using the same concept by using the dot. This is the syntax, and then at last sum of the values, that is 4, 1 by 4. So this is how we can calculate, how we can convert binary into the decimal form. This is the same procedure: 0.0, 0.010, 0.01, 0.25. These are the values 0 by 2, that is a 1 by 4, 2 by 8, 3 by 16, 6 by 32. This is the way how we can calculate binary into the decimal form. Now, next topic is your IEEE floating point representation. This is IEEE floating point representation standard for floating point arithmetic, that is IEEE 754, is a standard technical standard for floating point computation established in 1985 by the Institute of Electrical and Electronic Engineering, that is IEEE. Many hardware floating point units uses the IEEE 754 standard. The standard address many problems found in the diverse floating point implementation that made them difficult to really or reliably and totally use. The current version, that is IEEE 754 2008. This is the current version published in August 2008, includes nearly all of the original standard and IEEE standard for radix independent floating point arithmetic, that is your IEEE 854 1987. Now, let's say some characteristics or features of IEEE 754. First of all, it is defined by IEEE standard, that is 754/1985. It is developed in response to divergence of representation. Means whenever we have to represent the floating point representation, so that standard is maintained or given by IEEE, that is Institute of Electric and Electronics Engineers. Then it is portably issued for scientific code, means different scientists can use different IEEE code in different platforms or at different platforms like C, C++, Java, and this can be represented either in two forms, either in single precision and in double precision. This is how we can calculate. This is the example of floating point numbers. This is represent minus 0.75. So first of all, minus 0.75 equals to minus 1 power 1 into 1.1 into 2 power minus 1. So this is 2 power minus 1 into this one into this one. This is minus 1. 1 into 1 by 2. This is 1 by 2. This is 1. This is how we can calculate the floating point representation, or how we can represent the floating point representation. This is the example, this is the single example, this is the double example. Now, let's see in your book what is floating point representation. This is nothing but what I told you, that is IEEE for floating point representation. This says positional notation such as considered in the previous section would not be efficient for representing very large numbers. So that are not efficient for representing the large number. For example, the representation of 5 into 2 power 100 would consist of bit pattern 101 followed by 100 zeros. Instead, we would like to represent number in a form that is x into 2 power y by giving the values of x and y. This is how we can represent, and that standard is provided by IEEE. This is the standard. So this is nothing but the IEEE standard that is maintaining for floating point representations. This is a single precision and this is a double precision. This is exponent part, fraction part, exponent part and fraction part. Next is your example numbers. So first of all, takes 10 to 15 minutes break and then continue with your 4.3. That is your example number. So let's take 5 to 10 minutes break and then come back. So now let's start it with 4.3 topic, that is example numbers. This is nothing but the numbers or examples of the numbers which we have I have told you, like integer, arithmetic numbers, floating point numbers. So let's take this topic 4.3 example numbers. This says figure 33 shows the set of values. This is figure 33 shows a different set of values. This is how we can represent the number. This is denormalized, this is normalized, this is infinity. This is infinity, this is normalized number. These are the normalized numbers that are denoted by rectangle, and this is denoted by square, that is denormalized number. This is the infinity number. This is the complete range, that is plus 1, 0.8, 0.6, 0.4 and 0.2. Starting with a 0, here is plus 0, means all the values on the right hand side of the 0 is positive values, and all the values that is left hand side of the 0 is negative values, that is minus 0.2, minus 0.4, minus 0.6, minus 0.8 and minus 0.1. This says values between minus 1.0 and 1.0. That is negative and this is positive. These are the examples how we can represent the multiple number. This topic is nothing but only the examples of the number which I have told you. This is figure 33 shows the set of values that can be represented in a hypothetical 6-bit format having k equals to 3 exponents bits and n equals to 2 fraction bits. The bias is 2 power 3 minus 1 equals to 3. This is how we can represent the number. This is the example, as I told you, starting from minus 1 and ending with plus 1. There is a 0 on the left hand side, all the negative values, on the right hand side, all the positive values. This is another example for numbers. This is 0-bit representation. This is exponent part. This is 2 bar e. This is exponent part. This is fraction part, and this is value part. This is smallest force. This is largest denominator. Smallest denominator. 1 largest normalization or numerator or the normalized form, that is infinity. These are the examples. This is another table, examples of non-negative floating point numbers. This is the 0, smallest denormalized, largest denormalized, smallest normalized, and 1 largest normalized. Now, next topic is your rounding. So now 4.3 is nothing but examples of the above numbers. Next topic is the rounding, and this is one of the important topics, that how we can round the numbers. So rounding is a numerical value, means replacing it by another value that is approximately equal but has a shorter, similar or more explicit representation. So whenever we round something, So we can round by using a shorter, similar or simpler. Yeah, just a minute. There are different kinds of numbers like denormalized and normalized numbers. So this is denormalized number and this is normalized number, which are denoted by this one, which is denoted by minus sign. These are denormalized numbers which are denoted by positive sign, that are normalized numbers, and that are infinity means that is goes to the infinity. So denormalized means negative values, normalized means positive values. Right? So let's come back of rounding. So this is rounding as a numerical value means replacing it by another value that is approximately equal but has a shorter, simpler or more strict representation. Suppose I have to round 23.4476. I have to round up to two figures, up to two digits after decimal. This is 23.4476. So 4476, I have to round off this figure, that is 4. Then see the next one digit, this is 7. If it is less than 5, then this figure means the digit which we have to round up is the same. But if this digit is 5 or greater than 5, then the previous digit, that is 4, is converted into 5. Here 7, this is greater than 5, so this 4 is converted into the 5, means automatically add 1 to the left bit or the last bit or the last digit. This is 23.4476. Suppose I have to round off with 23.4476 with only one integer, with only one decimal point. So the output is 23.4, because here 4, now see next digit, this is 4, this is less than 5. So I am not round off the figure, not adding up the 1 to this. This is remains the same, 23.4. So whenever there is a value less than 5, then there is no changes, the same value will come. If the next digit is greater than 5, so that can be represented, or that can be represented with the addition of 1 value, or the fraction 312 upon 937 with 153, or the expression root 3 by 1.414. This is how we can represent, or how we can round off the figure. These are the examples. This is example, this is a fraction example, this is the expression example. This says rounding is often done on purpose to obtain a value that is easier to write and handle than the original value. So what's the main motto? What's the reason why we round off? To simplify the task, do not make the complicated task, make it easier to handle the original value. It may be done also to indicate the accuracy of a computed number. Means whenever we have to indicate the accuracy, means the accurate values of a computed number. For example, a quantity that was computed as 1, 2, 3, 4, 5, 6, but is known to be accurate only to within a few hundred units is better started as about 1, 2, 3, 5, 0, 0. This is a round of figure. This is 1, 2, 3, 4, 5, 6. This that does not look nice, because I have to round off. If I have to remember something, that I automatically remember the round off figures. So this is how we can represent, how we can round off, and what is the main motto of rounding off. To simplify the task, this is 1, 2, 3, 5, 0, 0. On the other hand, rounding introduces some round off errors in the result. Rounding is almost unavoidable in many computations. Means we have to avoid or unavoidable, especially when dividing two numbers in integer or fixed point arithmetic. This is unavoidable because automatic or when we divide, then decimal values come. So it is mandatory for everyone, for user, to round off the figures. This is when computing mathematical functions such as square, roots, logarithmic, signs, or when using a floating point representation with fixed number of significant digits. In a sequence of calculation, these rounding errors generally accumulate, and in certain ill conditions cases, they may make the result meaningless. So sometimes when we round out the figures, there is error may come, and that error is so huge error that makes the result meaninglessly. Meaningless meaning there is no usage of the result that is produced after rounding of the numbers. Now, what are the types of rounding? First of all, typical rounding problems are. What are the typical rounding problems? This is approximating an irrational number by fraction. That is example pi by 222 by 7. This is when we divide an irrational number by any fraction. This is an irrational number pi, and when we divide pi by 22 by 7, this gives an error. And these are the multiple types of rounding, like integer rounding, fixed point rounding, square root rounding, logarithmic rounding, and signs rounding. Then second point says, another problem is that when we approximately a fraction, we calculate the approximate fraction with periodic decimal expansion by a finite decimal fraction. Example 5 by 3 by 1.667. So this also gives an error. Another error is that when we replace a rational number by a fraction. This is a rational number, and we can represent, or we can give by a fractional number with the fraction. This is 3122 by 9417. This is 1 by 3. This also gives an error. Next, replacing a fractional decimal number by 1 with fewer digits, that is 2.1784 by 2.18. These are the multiple errors that we are facing when using the rounding function. Now, next topic is your floating point operations. This is the calculations purpose topic. The calculation is more important in this topic. This says arithmetic operations on floating point number consist of addition, subtraction, multiplication, and division the operations. So as I told you in the last class, how we can perform the operations on integer arithmetic. In the same way, we can perform the operations on floating point arithmetic or floating point numbers. The operations are done with algorithms similar to those used on sign magnitude integers. As I told you, which I was used in yesterday's class, that is sign number. In the same way, we can multiply or we can add the numbers with the use of floating point operations. Because of the similarity of representation, example only add numbers of the same sign. So the numbers are of opposite sign must do subtraction. Now, let's see how we can add the multiple points numbers or floating point numbers. First of all, example on decimal value given in a scientific notation. This is 3.25 into 10 power, that is star star 3, 2.63 into 10 star star minus 1. So first step is align decimal points. First of all, align the decimal point. This is 3.25. I can write is 0.000263 into 10 power 3, because this is minus 1, and I have to use the same format as the first one, that is 10 power 3. So I have to represent into 10 power 3. So this will be represented by 0.000263, because I have to divide by 1000, because 10 power 3 is 1000. The second step is add them. First of all, align. This is the alignment. Now add them. I can add 3.25063 into 10 power 3. Presumes use of infinite precision without regard for accuracy. As I told you, there is less accuracy in terms of addition, subtraction, multiplication in floating point integers. This is less precision and less accuracy whenever we add the numbers with the help of floating point integer. Now, third step is normalize the result. Normalize the result means already normalized. This is already normalized means normalization means fixing the errors or fixing any type of discrepancy in the output. So I am repeating again how I calculate. First of all, This is 3.25 into 10 power 3. This is 10 power minus 1. So my target is that first of all align the decimal point. So this, the second equation is converted into 10 power 3. 10 power 3 is 1000. So divide this number by 1000. This is 0.000263 into 10 power 3. Now second step is add these values. So I can add these values, and then third step is normalize the result or maintain the accuracy without any errors. This is how we can add the floating point numbers in computer organization or in computer architecture. Next one is multiplication. First of all, let's see example of addition again. Suppose I have to add the number. This is my number. This is 2.2 into 10 power 2. I have to add this number by 0.4 into 10 power minus 1. So first of all, I have to use this number. Well, this is a positive number. So first of all, use this number and convert 10 power 2, 10 minus 1 into 10 power 2. This is as it is 2.2 into 10 power 2. Now convert this figure, that is next figure, into 10 power 2. 10 power 2 is your 100. This is your 100. So this is 0.04 because I have to divide 4 by 100 into 10 power 2. This is alignment of the decimal number. Now add the number. This is 2.24 into 10 power 2. This is how we can add the floating point numbers. Right. Now next step is your multiplication. Example on decimal values given in scientific notation. This is example for multiplication. First of all, 3.0 into 10 power 1, 0.5 into 10 power 2. Algorithm. Multiply the Mantisas. First of all, multiply the Mantisas. So this is the Mantisa part. First of all, multiply the Mantisa. This is 1.50 into 10 power 3. This is also Mantisa. Then first of all, multiply the Mantisa and add the exponent. This is the exponent part. Add them. 2 plus 1 is 3, and I have to multiply this one, that is 1.50. Next example is binary. So this is how we can represent the decimal value. The main algorithm is that multiply the Mantisa part. This is the Mantisa part, and add the exponent part. This is 2 plus 1 is 3, and Mantisa part is 3.0 into 0.5, that is 1.50. Now let's take another example. Suppose I have to add these numbers. 3.4 into 10 power 8 into 2.5.
I have a box 20%.
Into 2.5 into 10 power 1. So I have to multiply these numbers. So first of all, multiply the Mantisa part and add the exponent part. So this is the same. This is 10 power 9 because 8 plus 1 is 9. This is 10 power 9 and multiply the Mantisa part. So multiply these terms. 34 into 25. In the same way, this is 0 to 17. This is 8 and this is 6. So now sum up. This is 850. This is 850 and put the decimal. So this is 85.0 into 10 power 9. This is how we can multiply the floating point integers. Means First of all, multiply the mantissa part and then add the exponent part and then route down the values. This is multiplication, this is addition of the exponent part. Now, example in binary term. This is example in decimal value, this is example in binary terms. First of all, use a mantissa that is only 4 bits so that I don't spend all day just doing the multiplication part. This is a very right concept. Just take only, use a mantissa of only 4 bits because this is very long calculation, but don't use any extra bit other than the 4 bits. This is how we can mantissa multiplication. I have to take only 4 bits, that is 0100, this is 0100, 1100, 1100. Right. So first of all use 000 because 0 is multiplied by 0, then 0 is multiplied by 0, then 1. 1 is multiplied by all these bits, that is 10100, then 1 is again multiplied by all the bits 101011. This is next one is multiplied all the bits 10100. Now in the same way which I told you in the last class, multiply and then add step by step. Adding step by step means first of all multiply and then first of all add first 2 bits, that is these 2 bits. The output is added to another bit. Next the output is added to another bit. Next the output is added to another bit. Means this will be done in step by step. First of all add first 2 bits, collection of bits, then output of that is added to next bits, then output of that is added to next bit. This is how we can calculate the multiplication. I am repeating again, multiplication of decimal point is easy, but in binary terms it is very difficult. So take only 4 bits. Don't waste any time. Take only 4 bits, that is 0100, 1100. Right. This is 0100, 1100. Now multiply all the bits by 0, by 0, by 1, by 1, by 1. This is how we can multiply. Now after multiplying, add all the bits in step by step. First of all take 2 collection of bits, then take another 2 collection of bits, another 2 collection of bits, and another 2 collection of bits, and then represent or add the values, and then the output is 10.00110000. This is how we can represent or how we can multiply the bits in floating point representation. Now let's see in your book. This is a rounding. As I told you, there are multiple types of rounding. This is round to even, round towards 0, round down, round up. There are multiple types of rounding that is available for dollar sign. These are the multiple examples. You have to round the figures. Next is your floating point operations. As I told you, there are multiple types of operations, that is addition, multiplication. Addition is done by using the adding the mantissa part, multiply the mantissa part, and adding the exponent part. This is how we can add the number x equals to a plus b plus c, y equals to b plus c plus d. Then next topic is your floating point in C. Till now we have covered how to use the floating point number. Now it's a time to add up or to merge the floating point number with the programming language, that is your C language. This is floating point in C. This says all versions of C provides 2 different floating point data types, that is float and double. Means whatever version of C that provides 2 different floating point data types, that is either float and double. On machines that support IEEE floating point, these data types correspond to single and double precision floating points. In addition, the machines use the round to even rounding mode. This is the representation, this is the crux how we can represent or how we can use in programming language the floating point number. The first line says in C there are only 2 types of data type that is used, that is float and double, and IEEE also provides some data type that correspond to single and double size precisions. And there is one round option used, rounding function used, that is round to even rounding mode. This is the syntax. This is hash define GNU source 1. This is hash include math.h. This is the header file, and this is the keyword or the macro or the syntax which I am using in define terms. This is the example practice question. Hash define post infinity, negative infinity, and negative 0. This is how we can represent. This is x equals to int double x, means assigning the value or checking the equality that has a value x into x. This is int double, means using the data type and compare with the x. Now next topic is a summary, but before this let's check on slides. This is by floating point in C. How we can represent the floating point number in C language. This is the program that returns the average of a list. So my main motto is to find out the program or write the program that returns the average of a list. This is first one line is double, then average int and int a. This is the array. So whenever we have to use multiple words, multiple digits, so I have to use the array, and array is denoted by square bracket. This is the function name average, and these are the arguments that have a data type int. This is a variable int n and int a, and there is a array. That means there are multiple kinds of numbers. This is the function name, means the program name is finding down the average of a list. This is int sum equals to 0. So first of all take the some variable that has a value 0, then int I, take another variable that is of data type int. Now use the loop, that is for. This is the statement which I told you. I equals to 0 means that first of all I has a value 0, then I is less than n. I is less than n means I is less than n. If this syntax, if this condition is true, then only my loop works, otherwise my loop does not work. So if I is less than n, I plus plus, then sum plus equals to ai, means adding the sum value and put into the ai. Return double sum slash n. So this is how we can represent, because this gives an average, gives an in floating point representation. So this is the way how we can represent the floating point number in C language. This is sum equals to plus equals to ai, means adding all the values of sum and then divide by the another number. That returns the average of a list. This is how we can represent the floating point number in C language. Next example is here, this one, hash include stdio.h, math.h, because I am using math function, that's why I am considering the header file, that is math.h, that is int main. First of all take float values, that is a equals to 5.375, take another variable, that is char pointer p int I, then use these values for representing the floating point representation. So I am using here 5.375, this is the floating point representation. So we can represent the floating point number with the help of C language. Now, next topic is here, summary. Summary means summing up all the values or all the content which we have represented in chapter number 2. This says, computer encode information as bits, generally organized as a sequence of bytes, because a collection of bits is known as bytes. So this says this encodes the information as bits that generally organized as a sequence of bytes. Different encoding are used for representing integers, real number, and character string. There are multiple encoding that are used for representing the number, for representing the integer, for representing the character string. Different models of computer uses different conventions for encoding the number, that is either bit by bit, either byte by byte, or either kilobyte by kilobyte. Next paragraph says floating point arithmetic must be used very carefully because it has only limited range and precision, and because it does not obey common mathematical properties such as associativity. So floating point can be used carefully because it may be give some errors whenever we find the average, whenever we can represent the number. So that gives an error because does not give or does not apply for associativity as compared to the integer arithmetic. So it is not mandatory to use floating point representation, but there are some scenarios where we have to use only floating point representation. So that gives only a precision and that gives some type error to the user. So till now we have covered integer arithmetic, floating point representation, and representing the information. These are the multiple examples which we have to do. Write a code for this. These are multiple examples. These are the examples that is available in your book. Now, next chapter is machine level representation of program. So in today's class, I will wind up with your second chapter, that is representing and manipulating the information. So let's take a quick review of the today's class and the whole section. In today's class, we have started with floating point, means what is floating point, how we can represent the floating point numbers. What is a floating point number? What is a syntax or what is a form used for floating point number? Which standard is used for representing the floating point number? That is IEEE, Institute of Electrical and Electronic Engineers. There are multiple types of formats, but some are known as basic formats and other are known as extended formats. There are multiple types of precision, that is double precision, single precision, and double extended precision. Then we have talked about some fractional binary number. What is a fractional binary number? That can be represented by 0 and 1, and there is also a decimal point representation. Then this is the fractional binary representation, how we can represent using the 1 by 10, 1 by 100, 1 by 1000, or 1 by 2, 1 by 4, 1 by 8, 1 by 16 when there is a binary representation. And when there is decimal, so 1 by 10, 1 by 100, 1 by 1000. Next, we have talked about the binary fractions, that is 1 by 2, 1 by 4, 1 by 8, 1 by 6, and 2 power 0, 2 power 1, 2 power 2, and 2 power 3. This is example how we can convert decimal into the binary form using the floating point number. This is IEEE floating point number. There are multiple features that is available for IEEE standards, that is 754. These are the examples. Then next topic is how we can round off and what is the advantage, why we are rounding the figures or why we are rounding the digits. These are the multiple examples. There are multiple types of rounding like integer rounding, fixed point arithmetic, roots rounding, allometric rounding, and science rounding. And these are the multiple problems that we are facing by using the rounding function. That is, whenever we divide irrational number by a fraction or any decimal number by a finite decimal fraction, that is 5 by 3, that also gives a problem. That is 1.6667. Because there is infinite 6, so I have to represent by 7 automatically, so that gives an error. Next is floating point operations, how we can perform the floating point operations or floating point number like addition, subtraction, multiplication, and division. This is the example for addition. This is the example for multiplication. Then how we can represent the floating point in C language. This is what we have covered in the today's class. Now let's see what we have covered in chapter number 2. In chapter number 2, we have covered only 4 topics. That is, first one is information storage, means where the data will be stored, what are the types of memory, that is primary memory, secondary memory, cache memory. Then we have also talked about how we can represent the integer arithmetic, integer representation, means how we can represent the integer number. Then in the next topic we have covered integer arithmetic, means what are the operations that we performed on the integer values like addition, subtraction, multiplication and division. Then we are talking about floating point number, means what is floating point number, how we can represent the floating point number, and then how we can represent or how we can perform the floating point operations like addition, subtraction, multiplication and division. Then we have also talked about summary, means what is the crux of the whole lesson. This is the chapter number 2. So that's all for today's session. In tomorrow's class, I am starting with chapter number 3. I am starting with our chapter number 3. That is your machine level representation of program. Means how the programs are represented by the machine level instructions. What are the codes used for representing the programs with the machine level instruction. So this is the way I will start with tomorrow's class, that is machine level representation of program. So that's all for today's session, and if you have any doubts then please text the doubt and I will answer you. And thanks a lot for everyone for listening carefully, and tomorrow we will start with chapter number 3, that is machine level representation of programs. So that's all for today's session. Thank you so much.